Good afternoon, everybody. My name is Shihan Chaudhary, and today I'm going to talk to you about my project for multiprocessor systems. What I decided to look at was shared resource contention and how that affects speed up. I modeled this system, I modeled a multiprocessor system that has shared resource contention using SymPy. And SymPy is a discrete event simulation tool, and it's available within the Python library. This was everything I'll be talking about today is based off of whatever SymPy helped me get. So this presentation covers 7 things. The first is the initial question, the motivation behind doing this in the first place. Second is the model, the simulation model, and how it's set up. Next are the results from all of this, and then I'll give you a little demo of what I did to get this. And lastly, we'll just discuss everything I did. Moving on to the next slide, let's jump right into this, okay? So there's 2 core questions, or 1 primary question, and then a question above that. And the primary question is, how much speed up do we actually get as cores increase once the shared bus contention is accounted for, right? Well, when we have to look at this question, we ask this broad question is, why am I simulating this, okay? And in a real world system, multiprocessor systems, adding a core doesn't always equate to a proportional speed up. And the reason behind this is because there's shared resources, such as like the memory, the bus, and such, etc. Right? These things are very hardware strenuous, and there's a limit or a cap that gets hit. Amdahl's law talks about that cap, right? It gives you a theoretical ceiling on how much speed up parallelism can buy you, right? And when we look at this, there's a formula and whatnot. What I wanted to do was build a simulation that reproduced this effect, and you would be able to see the bottleneck that is affected, okay? Or the bottleneck that is created, per se, from having an increase in cores. So, jumping into it, let's talk about the simulation model, all right? This model is broken up into 3 parts, okay? And the first being a job generator. This generator creates tasks at random intervals using the Poisson theory? Poisson process. And this will place, basically, all the tasks onto a shared queue. This will jump into the next part of the model, which is the shared memory bus, okay? And so before any task executes, it has to acquire a shared memory bus, and it's modeled with a capacity 1. So this is where all the contention happens, what this whole big question I'm asking is, right? It's part 2. Next, we get to the third part of this model, and that is the processor cores, okay? So the cores will pull tasks from the shared queue and execute them in parallel, but only and only after they are past the bus, okay? This is a relatively simple model, but it captures the core mechanism what I'm trying to talk about, and that is how multiprocessor system speed up is affected by resource contention. So let's talk about the experiment itself, all right? So I simulated 200 jobs with random arrival and service times. They were ran across various cores, all right? The first being a 1 core, second was 2, then you had a 4 core, and then lastly an 8 core. So they all had a same random seed for every run. This would allow for identical configurations across all the runs. And this would ensure that any difference within the completion time was purely due to core count and the bus contention, okay? And it wasn't due to random variation. Now, the speed up is completed or computed on this, what's it called, equation right here, and that's the one core completion time divided by the n core completion time. So from that, I'll give you the results. The results are pretty simple, right? It's with the one core, it was about 867 time units. The 2, 4, and 8 cores, the completion time actually drops. But then the key thing happens, and that's the speed up increases. And the speed up going in order of 2, 4, and 8 is 1.99 times. Then you get 3.9 times, and then you get 6.9 times. Now, if you notice, this tracks with Amdahl's law, and it's very, very close with the prediction count. There's a slight variance, and if you want to talk about that variance, let's look at the 8-core count, right? And so 97.8% of the workload is parallelized, but the remaining 2.2% is not. And this is the bottleneck that I've been trying to talk to you about. And this is where the contention happens, and it explains the gap that we get from the ideal lineup or the ideal linear speed up versus the simulated line and Amdahl's law line. This is the code I ran to do, all right, this just backs or just proves the data that I gave to you is real data. And once I did that, I also plotted for a graph. And that graph is shown right here, the speed up versus number of cores graph. The gray line is the ideal linear speed up, okay? That is what, in theory, is what's going to happen. That's the best way. The dark blue line that I show you is my simulated, and then the teal line right under that is Amdahl's. So when we talk about this, it's pretty much the same data as I showed you in the table. But the curve, the simulated curve sits almost exactly like the Amdahl line or the prediction that Amdahl gives. And in a realistic situation, right, they both would, because of the core limitation and the sharing limitations, they're both meant to diverge off the ideal line. And this is showcased within the graph. And it showcases also the accuracy and predictability of my simulation across the law. Lastly, let's talk about the conclusion. What was done? It was a pretty simple process. This was all done on SimPy, all done on my Mac terminal, and it was had really relative processing time. But what it did do was showcase my theory, or showcase the modeling of shared bus contention, and it matched relatively pretty quick to Amdahl's law and the prediction that was given, right? And my data, to reinitialize it, right, it's 0.9788, almost a near 100%, obviously not, a 97.8% parallelized simulation. What could I do to increase or better this simulation? I could vary the bus access time, and what that would allow for is create just a more realistic simulation. And it would also kind of explain the sublinear speed up in a real system. For something else I could also look at would be clearing the cache, or also just testing different uniform workloads. But overall, I believe my simulation meets Amdahl's law and the predictable line that it gives, and it's pretty close to the ideal lineup, and it answers the core question: how does shared bus contention affect speed up in a multiprocessor system? Thank you for your time.